we will go through them and grade them, okay? So that you feel more involved with the course. It's not just you sitting there and me talking or Professor Agnihotri talking. Learning is always a two-way thing. You need to put some effort into this, otherwise you won't get that much back. Right. For today, what I plan to do is to do the morning lecture now for an hour or so on looking at the pile instabilities. And you won't find this in any textbook because apart from the book I wrote, which I will show you a flyer if you want, uh, but it is essential, and a lot of companies in the around the world are using this as a quick check. Okay, it's not for design, but once you finish your design, you want to check your piles actually pass this criteria first, depending on the depth of liquefiable soil you're going to get, and it's a very easy calculation to do. Okay. Again, we will set something for this tomorrow, and you can have a go tomorrow evening and submit it the following day. Right. So, pile instability in liquefiable soils. Uh, Before I get into the topic, we have seen many failures like this. This is a very classic example where a fairly new bridge at the time, in 1964, the Showa Bridge collapsed like that following the earthquake there. This is the Niigata earthquake. I showed you some buildings yesterday from the same earthquake. And this bridge collapsed, and this kind of shocked the Japanese engineers of the time. And it's so much so they still study this bridge even today, the foundations, the soil profiles, and so on. And this, although we see failures like this, almost every earthquake I have been to in the post-earthquake reconnaissance missions, we find that pile foundations are getting quite heavily damaged. I'll show you some more examples. Even the Kobe earthquake, there were many pile buildings that suffered quite badly. So from 1964 till 2025, it seems the piles are still performing poorly and they're still failing, which means we are not understanding something the soil is trying to tell us. It's not the fault of the soil, it's our fault. One of the nice things about Japanese is that they don't kind of say, yeah, the bridge failed, let's fire the chief engineer and move on to the next one. That's not how they work. What they did was actually to extract the pile from the failed bridge. And on the top right there, you can see the extracted pile. And they actually very carefully mapped this. This is all published in the paper by Hamada, published in 95. And so the bent shape of the pile looks like that. So what used to be a straight pile ended up being quite curved, as you can see there. And they also very carefully mapped each span where the deck has collapsed on both sides, on one side, and what happened to the piles underneath. Okay? And one of the things they said was the ground, if you look at it, the river is in the middle of the Showa River, and the ground slopes like this on both sides towards the riverbed. And that's quite a common feature to have. So immediately in 2005 and 10, between 5 and 10, what they said was that they took this off the 1965 publication, saw the ground is sloping, and said, oh, the ground is trying to spread laterally, like was some of the things I was showing yesterday. And the same thing happened here. So the soil, as it's trying to flow past the pile, applied quite a lot of lateral pressure, and that caused the piles to bend, and that caused the decks to move, and therefore they collapsed. So this was the theory. And obviously, there's a lot of traction for this. And the Japanese rail authority, JRA, got into the act and they came up with a methodology on how do you estimate the lateral pressure due to lateral on piles due to the lateral spreading. We'll come back to that story another day. But basically, the soil flowing, causing the piles to bend and causing failure was what they blamed. Lateral spreading of the soil was blamed. Now, I had a student called Shubhi Bhattacharya. By the way, he's also in India at the moment doing lecturing at different places, but he is now a professor at Surrey. When he arrived, we thought we shall look at this piles and liquefiable soil problem carefully. And I had a hunch. The hunch was, sorry, I'll come to the hunch in a second. Similar things happened to this. I think I showed you this picture yesterday. This Harbour Masters building in Kandla Port is also supported on piles. And these are my own pictures. And you can see the building tilt about 10 to 11 degrees. And the pile at the bottom, luckily when we went, they excavated. Like always, the excavation hole is full of garbage, coke cans, and the rest of it. But you can still see the pile underneath here with damage. So what happened here is that this is next to the wall you're seeing. Building example is from the Kobe earthquake. Again, these are circular hollow spun piles. I see in Jalandhar there's a factory that makes hollow spun piles locally. So I thought, wow, I should include this slide. So these are very popular these days. It's very easy to make concrete piles which are prefabricated. They're hollow and the manufacturing process is quite nice and easy. So you can make these piles, and that's what Japanese did and supported their building on it. And again, they very carefully, after the building has failed, and basically this pile has broke there, it's formed a plastic hinge, and as a result, the whole thing could rotate that way, and obviously damage the pile on the other side as well. When you have groups of piles, it has to be a kinematically admissible mechanism. We'll come back to that in a second. So you can see the pile has clearly broken off at the surface. So as a result, this three-storied building suffered rotation, and this kind of this is one building they looked at, but there were like 20, 30 other buildings of similar size having same failure. And then the problem is, again, as I was saying, even the building survived the earthquake perfectly okay. Some cracks in the walls, nothing major. But after the earthquake, it ended up having a rotation of the slope is marked there, 1 in 18, 1 over 18. You can do the tan inverse and it will come to about, I think, at 10, 12 degrees. Same as the Kandla, put it on pile foundations, and they're all trying to fail in a similar way. Or then get, thank you. Can I have some water here? Straight away. Perfect. Thank you. Yeah, that should work. So when I first thought of the problem, having a long shower at home, it occurred in my head that piles are quite long columns, right? I mean, most piles are 20, 30 meters long, and no structural engineer I know would design a column which is 30 meters high and as slender as our piles. Only in very, very soft clays, people have looked at, will the piles buckle? That is really soft clay. But for almost all onshore applications, you never worry about buckling of piles. But then what I was thinking was that when the soil liquefies, we are basically saying all the soil is now turned into liquid, therefore it doesn't support the pile anymore, right? So this pile can buckle, and typically you would expect it to buckle like this, forming a plastic hinge there. So if you're looking at bending moment, That's P times delta is the moment you're applying. And the bending moment is maximum, is zero there, and maximum at the fixity location, just like a cantilever, right? So obviously you'd expect the base of the, and which means that if I put beta as 2, this will become 2L. And if I open the bracket, my buckling load will be, basically, this becomes 4, right? 2 squared is 4. So unrestrained pile head means a reduction of the Euler load by a factor of 4, okay, compared to fixed. Because this is done, I'll do the first bit. Pen or something is there to write on here? Oh yeah, there is. Thank you. I found it. So what Euler did is, if you apply a load P there, if the if both ends are pinned and I get this, then that length is L, then beta is 1. But if my pile is like that, so this is free to move, then this shape here, you can reflect it on the other side to make the same shape as that. Then this is 1L and this is another L, right? So we always try to make it like this by filling the shape. This is called the mode shape for buckling pile. I don't know whether you learned buckling like that or not, but this is how we teach it in Cambridge. Very easy. It's just pictorial, right? For other end conditions, we'll come back and do this again later on. So, for this case, you can see why L will become 2L, beta is being 2, which means I'll drop, compared to this buckling load will be a factor of 4 less. So, the smaller the buckling load, the worse it is, right? Which means the pile can buckle quite easily. Yeah. I'll come to that. I haven't finished this. Yeah, good question. We'll come back and you can say, if I missed any condition, you can tell me. Yeah. So basically, we can do this kind of equivalent length analysis by adjusting this beta to work out the Euler critical load. So LE is what you would normally call the unsupported length or the free length of the pile, and beta is the factor based on end conditions. That's what we are trying to do. So as I explained here, this is where beta will become 2. So 2 squared will be 4. That's why unrestrained piles are probably the worst. Suppose you got fixity on the top. Okay, as I said, I will not leave anything hanging out there. So this is what happens when I have a situation where, suppose I got pile cap, piles going like this, and I want to look at the buckling of this, then this one will have to bend like that, and this one will bend accordingly like that, and this whole pile cap will translate there. So this shape is what we are looking here. So from what I just said, if that is the shape, I'll try to reflect this again like that. So to get the buckling, I need to look at the point of contraflexure and look at that will be the buckling length. So the shape is like that. So I look for these points and see what that beta is going to be. And it turns out for that again this will become just beta of 1, because this is like a pin-ended thing we looked at there. So if I know the shape of the buckled column, I can work out the effective length of beta like that. You just need to imagine, reflect it to complete the shape and look for points of contraflexion. Okay, so this is when I have a stiff cap and a fixed base, I'll end up with a beta of 1. So obviously a pile cap with many piles will give you a higher buckling load. Right. So far, this is all in my head, right? So I dreamt of that piles will buckle during liquefaction because the soil is going to lose its support, but there's no proof. We only have piles in the field that have been pulled out that show a shape, but there is no, nobody was there when the actual earthquake happened and how the pile is behaving during the earthquake. Now that is the proof we want, right? So to do that, we will do this centrifuge testing. As I said, the theory will cover in the second lecture, but this morning, let's assume we know what this is. So the way we created the Shubhi's model, Shubhi Bhattacharya's model, is very simple. We got piles which are all fixed to the base, so they're rock socketed, and you put masses of different size on the top. So I'm changing my vertical load and putting on the top. So these are just like lumped masses on the top. In reality, they look something like this. Buckling loads are quite high. These are aluminum tubular piles, and you can see the masses of increasing size from right to left. And then we pour the sand and saturate it, put it on the centrifuge and shake it, creating the liquefaction. And this is what happened after the test, right? So here you can see all the piles buckled, but in forming hinges about here, here, and here. And he was trying to cut a cross section through the sand after the test. That's why to expose the piles. So you dig up the soil and see what happened to the piles. So this is like a visual confirmation of buckling, right? And if you remove all the soil, uh, these masses have been removed, but you can measure exactly where the hinge has formed. Of course, the whole point of doing these tests is not just see what happens at the end of the test, but get the data during, right? So we had pore pressure transducers. This is the picture taken after the test. You can see sand boils on the surface at different locations. As I said, that confirms liquefaction has happened. But we also have pore pressure transducers to measure the exact water pressure during, before, during, and after the earthquake. So here are the excess pore water pressures that are measured at different locations. So this is the shaking pit, and this is the post earthquake consolidation. So if you want more details, this paper is in Geotechnique. You can go look at it as well. Then we extracted the pile. I mean, he's done quite a lot of these tests, some with those circular masses, some with more concentrated masses, which are, these are just brass blocks on the top. And this is one pile that failed. He was very, very happy. He thought that we discovered something new, and he started going around the world, even does today, and present this. We discovered pile buckling. And great. I don't dispute. But also there is this other issue that piles will only buckle like this if the tip displacement into the ground is small. In other words, the piles have to be rock socketed. Now, not all piles in the world are driven into the rock and rock socketed. Many piles are just driven into dense sand. And when it liquefies, I had another thing in my head. Is it easier for the pile to settle or buckle? Is the question. Suppose you take a coconut, what's it called? Leaf, the spine of the leaf. Yeah, I know the Telugu word. I don't know the Hindi word. You take that and you have a bucket of sand. If you start pushing this into the sand, it will initially you can push it into the sand. At some point, it will stop going in and starts to bend or buckle, right? What is the depth? That is the question. I explained all this to Shubi, and Shubi said, no, 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 no. All piles in the world will buckle. I said, no, not really. And we had an argument, and we still argue about it. Then I had another question, and this was really a killer question for a PhD student. When we started in the very first slide I showed you, we were expecting the buckling to the hinge to form here at the base. But the bloody thing didn't do that, did it? It formed a hinge up here. Why? Obviously, from a structural bending moment point of view, moment will be highest here. But, and the whole soil has liquefied. I've shown you confirmation here. At all depths, we reached the full liquefaction values. So there's no question that the soil had not liquefied. It's clearly liquefied. So why is it doing this? He didn't have an answer, and I also did not have an answer until we kind of scratched our heads a lot more. So what we came up with is liquefied soil is not like liquid. It's not like a viscous liquid. It's something else. It is like a shear hardening liquid. So if it turns into liquid, fine. But if you want to move an object through that, it will go stiff on you. And the reason is, I can explain the reason on critical state framework. I don't want to go there now. But basically, if you are already liquefied, you have no strength. But if you try to shear that, it will try to create suction and therefore gain some effective stress. So we had the pore pressure data, and this liquefied soil reacts by dilating, causing excess pore pressures to drop and increase the effective stress. Okay, that's fine. So why is it forming the hinge here? So what the pile does is it wants to buckle the way it wants to, as I have shown. But the soil here, as it tries to move, will dilate and say, no, I don't want to do that. My effective stress has gone up. Then the pile says, okay, I'll try somewhere else, somewhere else, somewhere else. Only at this depth, this is close to the surface. Although the soil wants to dilate, the water can migrate there quickly and therefore suppress the dilation. And that's why it forms that hinge. So it has tried every section until it reached here. That's where it could fail. And we have seen this in many different piles. I'm just showing this as one example. So there is more to the piles in liquefied soil than first meets the eye. Okay. Now, is there a way we can calculate this? Luckily for us, structures people have solved this long before us. What they have done is create a chart like this. I adapted this just for piles, but any column you can do it this way. So for short piles or short columns, right, you will have this. This is the load you have to apply to fail the column in compression, pure compression, and that is the limit. So that for this type of pile is about 8,200 or some kilonewtons, and that stays constant. So that is the compression failure limit for the material of the pile. Fine. The Euler buckling load for unsupported lengths, you can pi squared E over Le squared, you can draw this line, and this tells you the reduction in your axial load as your pile gets longer and longer. So this is the compressive limit, this is the Euler limit. So far so good, right? Anybody not sure about this? You have done this kind of thing before? Hopefully, at some point. So for piles which are less than 7 meters for this particular diameter, uh, compressive failure is the problem. For piles greater than 7 meters, so that is about 7 meters. So greater than this, Euler buckling is the problem. Agree? But there is one other thing called Perry-Robertson's equation. What is this? Basically, what this is, if I have a column like that, and instead of applying the load in the middle, suppose I apply a load here. Okay, so this is called loaded eccentricity and happens all the time in structures. You make the column, and when the loading member comes on the top, that may not quite line up to the center of the column. So you'll always get some eccentricity. The other possibility is a lack of, say, the column itself has some kink in it, like that, just when you cast the column. All these will reduce your buckling loads, right? Because this is a imperfection, that is load eccentricity. All these cause some level of dropping in your Euler buckling load. And the way they calculate this is they calculate that as an eta and some x% of L over R. Now, L over R, L is the length of the pile, R is the, what is R? Anybody? Very good. You made my day. Radius of gyration. Gyration, but yeah. So this is normally, you can work it out for something like 0.003. You vary this number and see how your load actually drops. So you can draw a series of curves where we implement this into your Euler corrected load will be, yeah, I can do EI eta LE and with some reduction of eta. Eta should be here, I think. As I said, the maths is not the important bit, but you can accommodate that imperfection or load eccentricity into your buckling calculation. If you do that, we can draw a line like this, Perry-Robertson's equation, which shows that right from the offset, any eccentricity will drop. This was drawn for a particular eta value. But you can draw a series of these lines for different eta values if you want it. So instead of having a sharp change, what eccentricity does is makes this change gradual. So we can use the same concept for the pile buckling as well. So that's why I use the structures thing to manipulate it to fit to a 600-meter dia tubular steel pile. And what is quite dramatic here is how quickly this drops off. At very long pile lengths, the eccentricity doesn't make all that much difference. But at the short distances is where it makes big difference. And what do we have here? A very short distance, because this bit of the pile is more or less straight, right? So we are getting this much, this low level of plastic hinge formation because my of the load eccentricity I'm creating. Okay, so that's how you can explain why it has formed. So from soil mechanics point of view, soil dilation is the one which is stopping from the hinge forming anywhere else. But really, from a structures point of view, you can interpret that as eccentricity of load or imperfection in the pile. Yeah. Yeah. Yeah, that's right. Highest. So yeah, this is surface, shallow PPT, middle layer, deep. Yes. Ah, very good question. I like it. You really got into the crux of the matter. We expect this because all the fluid from this one can only drain upwards, right? So once the soil liquefies in the post-earthquake period, it has to reconsolidate. So the reconsolidation happens as the fluid comes from the bottom to the top because it can't drain. There is no drainage surface. The base is like a bedrock. It won't drain there. So that's why you get all this sand boil and the rest of it, and all the fluid is coming up, which means the shallowest layer is seeing that incoming fluid and that it stayed liquefied for longer. Very right. However, when the pile buckles also we know, right? So it did not buckle in this period. In fact, it buckled here. You can see where there is a thud, right? So each of those piles fell off during the shaking, not in the post-earthquake period. Does that answer your question? But very good question. That shows you're engaged. You know what's going on. Makes me happy. As a line, is it seems the effect of this eccentricity is almost like halving your Euler buckling load, uncorrected Euler buckling load. Right. So then normally you have two by two, or at least or 3 by 2. You form groups of piles and put a pile cap on that, and your column comes on the top. So single piles are very rare. So it's no point me having showers and dreaming about single piles buckling when the reality of the world is that you are always going to come across groups of piles. So we thought, right, we should try and do this properly for pile groups. So this was the next PhD student, Jonathan Knappett. And the first thing we did was, again, we dreamt up how the piles, this is a 2 by 2 pile group. Obviously, in section you can only see two, and there are two other piles behind. So how can these piles, these pile groups fail? This is what you call kinematically admissible mechanism. Have you come across that word before? Yeah, not you. You should stay quiet. You can get the other people. Answer. What is the kinematically admissible mechanism? Do you guys do upper bound, lower bound analysis? Anytime in structures? Senthil Sam is not here. Otherwise, I could have asked him. It's not, the word is probably more complicated than what it actually is. All it is that if this pile cap wants to go there, right, then all the four piles need to deform in a mutually agreeable way, right? It's like imagine a bullock cart with two bulls, right? Now, one bull, if it goes forward and the other one doesn't, then the whole cart will rotate, right? So that's not acceptable. So you made the, what is the thing called? The, uh, the crossbar that joins both the bulls very stiff, so that if one bull is not walking, it gets hurt, and therefore it walks the same way as the other bull, right? So kinematically admissible mechanism is like a bullock cart, where both the bulls or both the horses, whatever animal you choose, have to go together. And going together means kinematic means moving. Admissible means it's like a compatible way to go. And the same thing can happen in marriages as well. Both husband and wife need to go together, otherwise, it's a mess. We all know that. So, for piles, coming back to more our pile foundations, so if this cap wants to go there, I need four hinges to form, four plastic hinges to form. So, I need two hinges at the top and two hinges at the bottom, so that it can go, these two piles can go, and the same should happen for the other piles behind. So in a 4 by 4 pile group, you'll get, 2 by 2 pile group, you need to get hinges like this. This will be compatible if they, where I'm not allowing the pile cap to rotate. If I can allow the pile cap to rotate, then I only need three hinges, and I can have this kind of mechanism. So this is a four hinge mechanism, and that's a three hinge mechanism. Both are compatible in their own way. Only thing is, am I stopping the pile cap from rotating or not? So who's going to decide that? That will be decided by if I connect, say there's a column coming here, applying the load, another column here. So this is the ground level. If I make a cross beam between the two, what you call ground beam, then both of them can go, whole thing can translate, but it can't rotate. Individual pile cap can't rotate, because if this one wants to rotate, the ground beam won't agree. It will create bending moment, and that will be transferred to the other one. You've got structural stiffness. So this is one of the reasons why you can't do these kind of problems thinking, I'm geotech, your structures. The whole thing works together. And the solid structural interaction means that, right? So if I have this kind of arrangement, I'll get this. If there is no ground beam, if there isn't that, then I can get that. Is that clear? Okay? So these are obviously ways in which I imagined, along with Jonathan Knappett, that the piles, groups of piles can fail. because of liquefaction. So we created, again, very similar models, completely liquefiable layer, base is all fixed, and this is the instrumentation free field between the piles. And uh, he did these tests by adding these brass blocks. So we could change the vertical load depending on how many blocks we are adding. So G1, G2, G3 and G4 are more heavily loaded, so that we know what fraction of Euler load we are applying. We calculate the Euler load and say, I'm going to apply 50% or 70% of Euler load to create the buckling. Another problem with this is when you shake the model like this, what did we learn yesterday? The piles will have two types of loads on them, right? What are the two? Inertial loading and kinematic loading, right? Here, this is a bloody big block of brass mass on the top. So my inertial load is going to dominate, right? So, if I don't do anything, these will simply break the pile on the head because the inertia is so big. So the inertial load will dominate. But that's not what I want to study. What I want to study is let the soil liquefy and see if the pile buckles or not. How can I do that? We came up with this idea that I can support these piles on either side, the pile heads or pile mass, by having gantries that run along. So I'm not allowing the pile cap or the head mass to oscillate in this direction. It can only oscillate with the box. So it can't go further like this. It is stopped by these stops. I may have a picture of this. Yeah, you can see this is the uh, these are the bars which are running across. That's PTFE to reduce friction. And when the piles wanted to buckle, they could buckle this way. So I'm shaking this way, and there's no inertial load this way, right? But the pile group has formed failure this way. This is in plan view. So the shaking is happening in this direction. As it shakes, this mass wants to go back and forth, but these are stopping it from doing that. So I'm taking the inertial component out of the equation. So it's when you do these experiments, even when you imagine them, you need to have your head screwed on. Otherwise, you'll get something totally you didn't ask for. Anyhow, we'll come back to this. So these were the supports to stop that from happening. We got all the instruments, and you can again see in the free field, the pore pressures built up to full liquefaction level. The dashed line indicates for that depth what is the liquefaction pressure, and these are nearer the piles. This is the first time we started seeing this development of suction or dilation happening next to the pile. So my instrument was close enough. As we start to shake, the pore pressure builds up and then it drops, and then it recovers. Okay? This big thud you see here is when the pile mass actually went and hit the edge. So we can even pick up when the bang happened on the because the mass fell off into the liquid. Right. Now, pore pressures are interesting for geotechnical engineers. Structures people don't care one iota about pore pressure. That is entirely geotech problem. Or what they want is load and displacement, and quite rightly so, because the building depends on those. The pore pressure has been generated or not, who cares? They don't care, for sure. We care. So we had these displacement measuring devices. These are draw wire LVDTs. And for this G4 pile group, which is uh, yeah, G4 is the one with the heaviest load, which buckled. We could see that the displacement until the earthquake happens, nothing. Initially, the shaking happens, picks up a bit, and it's almost okay until here, and then it runs off. And that is as long as my device can measure. It doesn't mean it stopped there. That is the end of the stroke for the instrument. So, what I'd like you to focus on is this bit here. This one, we can, as engineers, we can live with. This kind of runaway displacement is impossible to stop. Also, this is why it is called a instability. Buckling, unfortunately, is it's an instability. You must have done fluid mechanics at some point in your lives. You know vortex shedding. So if I got a pier, bridge pier, water is flowing around behind the pier, you get vortices, right? If the flow velocity is big enough, this vortex suddenly leaves the pier and starts doing that, the whirlpool thing. And when it leaves and goes down the river, is nobody can predict it. And that's called an instability. That's a flow instability. Same thing happens with airplanes and the vortex shedding behind the airplane, which will affect the other aircraft. That's why these days, the end of the uh, uh, wing, they bend it upwards, if you see, and the bend reduces vortex shedding. It's more continuous. That's why they're all bent up. This is something people have learned in the last 20 years. So now all airplanes have the end of the wing being lifted up. So instabilities in engineering are real problems because we are not in control. Yeah, sorry.
Suppose if we are controlling the drainage, that instability, sudden increase in displacement can be prevented.
I don't think so. Because this happens so quickly, it is almost like an undrained event. So it is trying to shear off the soil and go, right? So when the soil is in that mood, when the structure is in that mode, soil really can't do much because soil needs time, right? So if something is failing, even when it's an undrained event, by controlling drainage, you will control more long-term behavior, making it more from drained to partially drained to drained, fully drained. So we can't really control this using just drainage. But sorry, if you can prevent the poor pressure from building up in the first place, then you have a chance. But once you are in that mode, as I feel it is unstoppable. But again, you're welcome to do more research and come and tell me. You can stop it. I'll be happy. But as far as I know, that is quite difficult.
Because if we are controlling core water pressure is below 0.6, like we can displacement is less than 1 m.
Don't you, in this case, the displacement is controlled by how much load on the pile, right? When you are putting loads close to oiler load, then uh, all those rules don't work. What you're saying is for small pile with marginal head loads, then you can control. But these are piles which are getting close to buckling. So, no, is the answer. Okay. So this is the classical picture. If you buy my book, this is what we used for the cover picture. This is, we extracted this pile and lo and behold, where did I have my hinges when we started? We had two at the top and one at the bottom, even the three hinge one. I can go back. Let's remind ourselves. Oops. hinge there, hinge there, hinge there, assuming this pile is going to be straight. Or 4 hinges at the top and bottom. Did my pile do that? No. And this is why experiments are fun. You think you start by knowing something, and every time we do a centrifuge test, it comes back with some other thing which makes me think. And that is the beauty of doing experiment. If experiment is done knowing the answer, there's no point doing the experiment, right? You already know the answer. So you got to go do this with open mind. So what has it done? It's done hinge here, hinge there, and hinge there. Obviously, these are allowed to, the pile cap is allowed to rotate, right? That is the, so it only needs 3 hinges. So our guess that we need 3 hinges is right to make a kinematically admissible mechanism. However, the location of the hinges is, we are not even close. You can see. And this bothered me. This is here, that is up there, and that's up there. And for a long time, we didn't know how can we predict this. I mean, for most structural engineers, the fact that plastic hinges forms means the structure is dead, right? So they don't really worry about the location of the hinges. But from a science point of view, you really want to know. This is a model we created. The sand was poured by hand. The saturation was done in the lab. Relative density perfectly measured. And if I can't predict what this is doing, what chance do I have for real structures with so much stratigraphy, site variations, and all that? In the lab, when we are making perfect models, we should be able to predict this properly. Otherwise, what's the point? Anyhow, that's my take. Poor Jonathan had to work much harder. By the way, I'm putting the things, yesterday a professor was saying, we got this BGA medal and the TK medal, we won 3 times. 2 of them were for the single pile work and the pile group work. Both got the same award 5 years later, because one proves for single pile and the other one does for experiments. By the way, if you do them well and come up with good explanations, are very attractive, because only you have the data and people can appreciate that, oh, the experimental work is hard. Numerical people always struggle because there's a saying that for experimental research in geotech, everybody in the world believes in your work apart from you, because you've done the experiments, you know what's wrong with it. But everybody in the world says, yeah, this is data, this is good. Numerical people, only you believe in your result, the rest of the world doesn't believe it. So it's the opposite of the experimental work. This is like a common saying in research world. Anyhow, so this, although was a nice piece of work, left more questions for us. Oh, this is on UPS. Great. You can carry on. So we thought we'd try and have a go at doing this numerically. Not the whole shaking and the rest of it. We tried to simplify the problem. And is that telling us the power is not there? Okay. We can ignore it. It's not that building is on fire or anything like that. Okay. So we model this in Abacus. Abacus is a very nice software, and it allows you to do things which are you can control a lot of things. So my pile length is like this, discretized, and we have these springs at different depths. This is classically how you would do PY analysis. I'll come to PY analysis tomorrow. But basically, you got soil springs horizontally, and these are basically Timoshenko beams, discretized. And you also can put the mass, the center of mass at some height, and some rigid elements to join. Now, what we do is, depending on the depth of the element, you change the PY curve. So P is the pressure that the soil applies on the pile, and Y is the displacement of the pile element relative to the soil element. So this is why, as I was showing you yesterday, if the soil does one thing and the pile does something else, the difference between the pile movement and the soil movement at every elevation is what creates the pressure. And that's what PY curve is trying to capture. So you start like that. So typically you say, I got some limiting pressure I can reach. It is like the passive pressure. And that is mobilized with the relative displacement along the x-axis. So the shape is typically like this. And it's not just me, there are lots of other people who have this data except Kyle Rollins, who got this completely wrong. And if you are interested, we'll discuss about what Kyle did wrong later on and why it is so. But this is the most accepted shape. So if my displacements of the piles are very small, I can basically get some non-zero resistance in the liquefied soil. Now, as the pile starts to deflect or starts to buckle, you shift to this kind of shape where I get increasing resistance up to a limit. And if I go next, so when you got the if I join these two, I'll end up with this type of this shape. So the size of this will be scaled from top to bottom, increasing with depth. Because if my confining pressure is more, I'll get bigger P compared to shallow depths. So we model this using basically that concept. And again, this is in geotechnique as a second paper of that. This was 3 times harder than doing centrifuge work. And it did not get one prize, one award, one mention by anybody. Because, as I said, we really believe in it, and other people said, yeah, 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 whatever. Numerically, you can show whatever you want, which is unfortunate. So, we created this combined spring of that shape, and you scale it depending on your confining pressure. That's our springs. That's all we have. We change the vertical load and the load eccentricity and see at what point the piles will buckle. Okay, so all I'm doing is apply that load, change for a given eccentricity, change my PY curves until the pile group buckles. You understand? Very straightforward, no dynamics or no shaking or anything. The key point about this analysis is the reason we chose abacus is if you try to do this, say, for example, in Plaxis, as soon as the pile deflects a bit, Plaxis will throw its arms up and say, I don't know what to do. The typical FE programs can't handle large deformations or instabilities. That is well known in FE community. I started my life with Professor Chandrasekharan as a finite element person, so I know what FE can and can't do. Centrifuge modeling I learned in Cambridge, but FE I learned in IIT Bombay, and quite well too. So we know what it can and can't do. Instability problems you can't solve. So when Jonathan came back to me and said, oh, I want to use abacus to model this, I said, no, you can't, because FE codes can't handle instability. Then he went back, came back with the manual for abacus, and he said, oh, they introduced this, what is called Rick's algorithm. The reference paper is there. And what Rick's algorithm does is it allows you to capture instabilities within abacus. This is why abacus is a good code. So because it's structural, written for structural engineers, it has a lot of these which structural engineers need. Post-buckling analysis, it's called. Great. We took that, and all it is trying to do is if my displacement versus some load factor this is a load proportionality factor. So this is the one we are increasing. So as I increase that, the displacement increases, and I'm going along this curve. So as long as this is increasing, every FE code in the world is happy because it's a positive stiffness. So the stiffness is always increasing, so it's cool. It's happy with that. When this thing starts to hit that and starts to fall off, if I draw tangent to this, that gives me zero stiffness. At that point, normal Flaxis and the rest, or FLAC, any other program, will throw its arms up and say, sorry, non-convergence, I can't work with this. And beyond that, as the pile starts to buckle further away, it will actually get into negative stiffness. Not just zero stiffness, it gets to negative stiffness. Negative stiffness is even harder to handle. So the way they handle this is, if you're here, you draw a circle with a given diameter, given radius. And then it says, I'm going to draw a tangent here and see where I am. And then it increments step by step. This load increment is reduced to very small values until it brings it back onto here. So if I reduce this diameter, it can search there, then here, then here, then here. So without upsetting the FE, it can still track the post-buckling behavior by reducing that increment to very small values. So that's the theory. Can it work for our problem? Yes, it can. And here are some predictions. So this is the curve we get from, so this is normalized, applied load normalized by the Euler load. So 1 means full buckling no matter what. And what we can see is even at lower values, it can buckle because of the eta I mentioned earlier, the load eccentricity. So we could track this and show when we expected it to buckle, it buckled. Where the Euler load is lower, it did not buckle, and the whole thing kind of worked for. I mean, we're changing the lengths as well. So our experimental results plotted on this quite as expected. And for each case, we could also look at the load versus displacement. This is their for shorter deflections, you can see that you get shapes like this, and our centrifuge data is a point that falls here because ours is just one delta we applied, right? Okay, that's not too far. So for short piles, the soil resistance is of less consequence, and it's more or less a structural problem. And when you have high soil pile interaction, then the pile dominate the response. And we can see again where our centrifuge data is and where these curves are for different analysis that were carried out. And finally, for really large strain between the soil and pile, the interaction is strong. And you can see this peak jump is because of the dilation effect in the soil. Again, our data, I4 falls there, just for reference. So it's broadly capturing what we wanted it to. But the real proof of the pudding is this. So this is a pile group which we tested. And here you can see the hinge formed here, here, and there. So, sorry, here, there, and somewhere here. And because this is an FE analysis, we could see where the bending moment has reached the MP value, plastic moment capacity value. So that corresponded to, from the analysis, it corresponds to these places. You can see how the bending moment is changing. These are the plus MP, minus MP values. And that corresponds perfectly to what we have got from the experiment, more or less, not perfect, but close enough. So As you can see, this type of analysis takes quite a long time to run and quite a lot of thought has to go in. In fact, this is probably harder than just doing the centrifuge test. Each has its own difficulty, but with the centrifuge test, the pain in all finishes in 3 weeks. 2 weeks to prepare the sample, 1 week to do the test. In fact, the earthquake takes about 10 seconds. You got your data, you go away, and you're done, right? The real hack starts how to interpret the data. With FE, you won't get anything for months, and you get all the results in the last 10 seconds, and then you're done. So you got to be, each has its own difficulty. I've done both, so I can tell you with some confidence. Right. In summary, I hope you found this interesting. So pile instability can occur when the soil surrounding the pile liquefies. I hope you all agree with that now. Yeah? Single piles can buckle and we can very easily estimate the buckling load. In fact, I'm going to ask you for a given pile, you got to come up with the structural properties and estimate the Euler load. I'm not going to ask you to do the Perry-Robertson's formulation. I don't know whether you're taught that or not, but if you're not taught, it would be based on that. Pile groups also can buckle if sufficient end restraint is provided. For both single piles and pile groups, what is the necessary condition for the pile to buckle is really pile tips need to be having zero displacement. In other words, they need to be embedded into rock. Rock socketed piles, you should definitely check. For whether you go to do the same check for very long piles which are going into dense sand, we'll see about that in later lectures. But that is something we should do. It's very easy check to do. It takes you 10 minutes to work these out. So why don't we do it? And this is what routinely mods and everybody else are doing in the UK. Numerical modeling can be done of this post-buckling behavior, and it is really with advanced numerical analysis formulation is required. So luckily in Abacus, this post-buckling deformation can be tracked using the RIX algorithm is already implemented, so you can use it, but most other software platforms don't have that kind of thing. Abacus is particularly advanced structural software. It's not just structural, it's general purpose FE. You can do thermomechanical modeling also in it, but it is very versatile. You have software license for Abacus, sir? You have? Wow. It's not cheap. It's like 2 lakhs per year or something is the fee. Even in Cambridge, there are like all my engineering colleagues, whoever are using, we need to contribute every year to keep the institutional license going. ONGC is so rich. What are you mourning about? Yeah, yeah. Oh, the industry rates are much higher. I know that. Okay, very good. Time for tea. Is called critical state. Critical state means the soil has reached a state where you can apply under the same stress, it continues to deform. So you gain strain without no further increase in stress, which means it's same as in plasticity, you reach the plastic limit and you therefore deform without any further increase in stress. So from this, what we can learn is soil is highly nonlinear, and also if I unload it, it's not going to come back. So if I unload from here, it will probably come here. If I unload from here, it will probably here. It never comes back to zero. as I said, we talked about earlier. Okay, so this is, you probably have this data as part of your lab even. Now, suppose I want to model this soil. Typically in civil engineering, what do? You can scale down models, right? So, and build a nth scale model, maybe 1 in 100 or 1 in 50 scale model, and you'll test the model. For example, I don't know, what would you have done? I don't know if you've done any bridge engineering or something. Say you want to model the flow of a river in hydraulics. What you don't do hydraulics lab, where they would have scaled all the critical values are the same. Normally, like the Reynolds number, Rayleigh number, hydraulics is full of these non-dimensional numbers. So you may make sure that the model and the real prototype have the same Reynolds number, typically. Thank you again. You're an angel. I had bad throat, so I'm struggling through the lectures today. Anyhow, so that works for hydraulics. People do something similar in structures as well. You can scale down models and build them and test them in wind tunnels and stuff if you want to look at the vibrations of bridges. In soil mechanics, we got a problem because if you scale everything down, our stress and strain are going to be, small model is very high. It's almost vertical. So the stiffness is, small model is very high. It's almost vertical. So the stiffness is very high. And you say, right, I built a model, say I built an earth dam, and I want to predict how much the model settles. I can measure it. And then I want to use that to predict what, when I build the big dam, how much that one is going to settle. So if I use this, I get say 2 millimeters of settlement. It's a 50 scale model. I'd predict that my actual prototype is 50 times more. So I'll get 100 millimeters of settlement. That would be your prediction if it's all linear. But because this is all non-linear, the actual stiffness you get will be this and that, right, for dense and loose sands, which are a lot smaller than this. So when you end up actually constructing the dam, you'll see that the dam in the field has settled maybe 300 millimeters or 400 millimeters. And you say, whoa, that means something has gone wrong. So we know this already. This is why we don't build small scale models in geotech and try to predict what the big thing will do. So what can we do to fix this? So you understand the problem. Anybody not sure what I'm talking about? So we know what is going to go wrong here, right? So we can't do small scale models. However, if I can get the stress and the strain in the model same as in the big field structure, prototype structure, then I'm in business, right? So we need to find a way to create the same stress and same strain as in the real structure without actually building the real one. Of course, you can always build the real structure and find out how much it settles. But by that point, it's a bit too late, right? Because you spent all the money, went and built the structure, the thing settled or even collapsed, and then you lost all the money. So that's not how engineering should work. You must be able to predict beforehand what it'll do. So basically, centrifuge modeling is a way of doing exactly that. And the principle of centrifuge modeling is so easy to understand. It literally can be done on the back of an envelope. So let's assume that we got a rectangular block with dimensions L, B, and H. And let's assume that the mass is M. And it's under normal gravity, 1g. So if I asked you to work out what is the pressure this block is going to apply on the ground, what will you say? M times G is the weight, and the area that is sitting on is LB. So my vertical stress simply should be mg over LB. Easy, right? Exactly same way, if I want to define strain, some change in length over original length is how you define strain, right? So alpha is some characteristic length, and therefore epsilon is change in alpha, delta alpha over alpha. Now just imagine that I have another block which is scaled down by a factor of n. So the length is now L over n, breadth is B over n, height is H over n. That's all we did. We squashed the block by a factor of n, all dimensions. So I ended up with a smaller block. Because all the dimensions are n times smaller, the mass of this must be this big mass over n cubed. Agreed? Because all the dimensions are factor of n smaller. Now, just for a minute, let's imagine that we're going to put this block in a gravity where the gravity is n times bigger. G is your acceleration due to gravity, but for this block, we somehow will make it sit in n times the normal Earth's gravity. If you can do that, let's calculate what the pressure this block is going to exert. So the mass is m over n cubed, and the gravity here is n times g over length is L over n, breadth is B over n. And as you can see, all the n's cancel out, and I recover exactly the same stress mg over LB as I had here. So although this block is smaller, because the gravity has been increased, it will also apply exactly the same stress. So the soil below this block and below that block will think that they are exactly being subjected to the same stress. Easy, right? Imagine why we couldn't think of this before the lecture. It's so easy, anybody can think of this. What about strain? Same thing. The change in length will be smaller because the model is smaller, but so is the original length. Again, they are smaller by the same factor, n. So again, you cancel these n's and I recover the same strain. So between the prototype and the model, we get the same stress and same strain. And that is what centrifuge modeling is. So how can we increase the gravity is the only question we have. One option is we can send our model to Jupiter. Jupiter has 32 times Earth's gravity. So we can use a scale factor of 32 and do all the tests on Jupiter. Unfortunately, space travel is very expensive and no civil engineer is going to get funded for that. Let's forget that. We need to find a way of creating high gravity on Earth. But we learned this in your school physics that if I put an object and rotate it with an angular velocity omega, then I'll get a centrifugal acceleration of r omega squared. Anybody who doesn't know this? Otherwise, we have to go back and check your, not the gates, what score do they get? JEE score, is it? If you don't know that, we'll have to go back and check the JEE score again. So this is very straightforward. So all I have to do is to create an object that rotates, and I'll organize the angular velocity omega such that if I want ng should be equal to r omega squared. R is the radius at which I'm going to hold the model and spin. That's it. For example, there is a centrifuge. I'll show the picture in IIT Bombay, which we helped build. And say you want to do a test at 100 times the Earth's gravity. So the left-hand side will be 100 times g. The radius of the centrifuge in Bombay is 4.25 meters, and the omega I can work out. That will come in radians per second. I can convert that into RPM by just multiplying by divide by 2 pi, multiply 60, I'll get RPM, right? So I need to spin the centrifuge at 145 RPM. It's not even that fast. Your washing bin machine runs much faster during the drying cycle. However, the issue is how big these things are. So this is our Cambridge machine, and this one is 10 meters in diameter, and it was built by, designed by a guy called Philip Turner, and that's why we call it the Turner beam centrifuge. 3 months ago, it turned 50. We celebrated its 50th birthday, and it's still working. So that is where I started my centrifuge testing career. I was a numerical modeler and up till that point. Uh, but there are bigger machines. This is the University of California Davis machine, where the Americans always must have bigger, right? Their radius is our diameter. Okay, it's not big, but it actually rotates quite slow, and also it has a big shaking package on the end. We'll talk about that later. So you can simulate earthquakes on this as well, and on our machine as well. But it is big, and that's not even the biggest one. The Army centrifuge is the biggest one. This is the U.S. Army waterways in Vicksburg, in horrible, horrible Mississippi. If anybody of you are thinking of going to U.S., I suggest you look at the pictures of mosquitoes in Mississippi. They are close to small elephants, but they fly and bite equally hard. US is not all this dreamland, by the way. So I spent for my sins 3 weeks on this machine when they were constructing it. And again, this is a 700 G-ton machine. Most of the centrifuges are classified as G-tons. How many tons of soil it can carry and what is the G it can go up to. Our centrifuges can carry 1 ton in Cambridge and can go up to 150 Gs. So that is a 150 G-ton machine. This one is a 700 G-ton machine. So this can carry a soil of 2 tons to 350 G. The Bombay one is a 200 G-ton machine, if my memory serves right. About 3/4 of a ton up to the 200 G, I think. There are other centrifuges. The ones I showed you till now are all in for research in universities. I should have the Bombay one also somewhere. I'll come to it. This one is special because the Japanese decided, when my professor Andrew Schofield was trying to make it popular, centrifuge modeling, they used to come to Cambridge even when I was a student, look at everything, take photographs, and they went back and built their own centrifuge. Takanaka is a big construction company. For them to build a centrifuge, they build buildings which are 100 floors high, and big bridges. So building a centrifuge is like easy for them. So they built this machine, and they do, for every project, they do centrifuge testing and numerical analysis and submit 2 reports by the time they come to tender. So you can see where construction industry in Japan is compared to where we are. Here you're lucky to get some analysis by the time you go to tender stage. Oh, this is the beautiful Bombay machine. It's a very nice picture BVS has given me. Homemade, built in India. It was Atmanirbhar before Atmanirbhar was invented. This was constructed about 25 years ago. And Chandrasekharan wanted to build this all. It's built by a company called Mekong, which I don't think it exists anymore. But it's a quite nice machine and it's quite robust. The reason I'm in India at the moment is we're trying to get an earthquake actuator for this. And with a little bit of luck, by January, we should be able to do earthquakes on this. We'll see. There are other type of centrifuges as well. Like we have a mini drum centrifuge where instead of having just one model, you can make the model all the way around, just like your washing machine. You put clothes everywhere, not just in one end, right? It actually balances it better. And for some problems, this is quite good way of doing this. And that's the sand pourer we designed in Cambridge. Okay, where are we in the world? Centrifuge modeling, when I started, every time we had to say, every conference, every seminar I gave, people will say, yeah, it all sounds good, but can it do that or can it do this? And we don't believe it and all that kind of stuff. But now I think after 30 odd years, I wrote a book on this centrifuge modeling for civil engineers, if you're interested. Maybe your library has a copy, and it's now accepted as a reliable way to investigate complex geotechnical problems. There are over 85 centrifuge centers around the world, South Korea, China, everywhere. In India, we only have one, but there are several IITs and other places trying to get more centrifuges. One of the nice things about this area is every 4 years, like World Cup cricket or World Cup football, depending on what's your taste, we have a conference and we all go and meet at some nice location. The last one was in Daejeon in South Korea. And the nice thing about this community is if I develop something, I'll go and present at that conference, and everybody else can copy that, imitate that. We don't mind. So we don't compete on hoarding technology, we share the technology. And where we compete is in bidding for projects. That is different. We are developing, these are all just tools. In the end, you should make your money by your brain. So, what is the new thing I modeled, or what is the problem I'm trying to solve? So, it's not about technology, it's about the problem. We also have a journal now, it's called International ICPMG, and you can publish papers there. So, it's kind of established, is what I'm trying to say. Right. This is a slightly esoteric slide, and it comes from my PhD thesis for some 30 odd years ago. What I studied was a tower structure on liquefiable soil with a raft foundation, and I wanted to see what the rocking behavior of this is. So, several floors high, and so on. Now, I talked about scaling this down, right? This is the actual full size field structure. Use scaling laws to simply to reduce the size. So this is the exact 1/nth replica of that. Now this one will be maybe 30 meters high, and this one will be maybe that high, right? Once you scale it by a factor of 100. Now, in this sized model, I can't create windows, doors, the column joint stiffness correctly, and so on. Yeah, it'll be difficult. I can't actually scale all the structural components exactly right. So, what we don't do that. What we do is you got to think here, what is it I'm trying to model? What I'm trying to model is the rocking of this. When the earthquake comes, this whole thing shakes and rocks. So I need this building to the same as that. But if I simplify that to a cantilever beam with a lumped mass on the top, then I should be able to uh, capture the rocking and the sliding behavior correctly. So instead of spending time making intricate models like children, we simply construct this. This one will have the same flexural stiffness as the big building and has the mass at the right location, and that's all I need. One extra step we got to do is to go from here to here. What this is if this is the centrifuge model I ended up with, I should scale this up and see what it looks like. Yeah. So if I scale this up, it looks like this. Then I look this and this and see what did I lose. Okay. And this is very important because if I started with an elephant, did all this and came here and it became a monkey, then you can't say monkey and elephant are the same, right? So at least the elephant should have 4 legs, big mass on the top, trunk in the front, center of gravity at the right place. It should look similar. It may not have the same shape, but it certainly should look similar. If the species is changing and it suddenly grown a very long tail, like a monkey, then something has gone wrong and you got to go back and do the model design again. So when we say prototype, we generally mean this. That is the full scale field structure. This is the prototype. Right. Now, we are not doing this scaling thing just for fun. What we want to do is to link what we can see in the model during an experiment and predict what the real structure will do. That is the aim of the whole exercise, right? So we need some rules or laws that link the behavior observed in the model to the field structure. So these are called scaling laws. But we already know several of these. I'll list them in a table. We already derived stress and strain. It should be the same in the model and prototype, right? So that is one. Length, we said we'll squash the thing by n. So 1 over n. Area is 1 over n squared. Volume 1 over n cubed. Mass 1 over n cubed. Acceleration n times larger. This we already know. So I just put them in a table. So these are the simple scaling laws. Now, what about things we haven't considered? For example, force. And this is very interesting because often in geotechnical engineering, you want to test piles. And pile testing is quite expensive, especially if you want to apply a lateral load on pile. The whole thing costs, I don't know, maybe 20 lakhs, because you need to have a reaction frame, push the load, apply the load to the pile, see how much it deforms, measure the displacement, measure the force. In the field, it costs a lot of money. But let's see whether we can do it better in a centrifuge. For that, I need a scaling law for force. But what do we know about force? Force is mass times acceleration, right? So force is mass times acceleration. So 1g and the acceleration as a. In the model, the mass is m over n cubed, acceleration is n times bigger than g, right? So if I want the ratio between the force of the model and prototype, I divide one with the other, I'll get 1 over n squared. This is quite in our favor. Why? Let's see. Suppose I need to apply something like 200-ton load onto the pile cap. Now 200 tons is like 2 meganewtons in SI units. If I'm doing a test at 100G, then the force I need to apply in the model is 2 times 10 to the power of 6 newtons, mega is 10 to the power of 6, divided by 100 square. I only need to apply 200 newtons or about 20 kilogram force. So suddenly I can apply these loads using little actuators in the centrifuge, and I'm modeling something that is very much bigger. So we can do a lot more testing like this and determine pile load tests easily. There's something even nicer. I believe you learned a little bit about consolidation, and consolidation of clays is one, I can say, the bane of geotechnical engineering, but that's where we make most of our money too. Because people want to put embankment buildings on clay. They want to know how much it's going to settle 10 years, 20 years time from now. And we say we'll pull out the pen and paper, do the calculations, and say, this is our best guess. But very often the embankment settle more than what you calculated 10 years. That's why even the road that are being constructed now, they settle a lot more in 5 years than you expected, creating potholes and whatnot. However, the theory for consolidation is quite mathematical, very easy. When you put a load, if the pore pressure increases, you call it U. So dou U by dou T is the rate change or time change of the pore pressure. You link that using a coefficient of consolidation to second derivative spatially of U in X, Y, and Z directions. Great. And we can solve this PDE until cows come home. But that's not how geotechnical people work. Basically, you work out what is called a time factor. You again should know all these things. And that you will say is CVT over D square, where CV is the coefficient of consolidation, D is the drainage distance, the distance to the nearest drainage path. T is the time it takes to get consolidation. Basically, TV tells you to get 90% consolidation, how much will the T be? If I want 95% consolidation, what is the TV factor? And you can work out the time for that. Obviously, these things take a long time, right? Now we want to model the same thing in the centrifuge. So I wrote the same equation at the top for prototype and here for the model. Now, what I want is the left hand side of both should be the same, because the model must have the same degree of consolidation as I would want in the field. Yeah, so TV should be, the time factor should be the same. Also, if I use the same soil as in the field in my model in the centrifuge, CV should be the same, right? That is just it depends on K and E naught. So K and MV, I guess we call it E naught. Anyhow, that is the same. Then the only things that are time and the distance for drainage. So we did that. So if I now get the ratio between time for model and prototype, that will become D model over D prototype squared. Again, the model is 1 over n times of that of the prototype. So my time for consolidation also scales as 1 over n squared. Right? Now let's have a go. Suppose I got marine clay, 10 meter thick, of the Mumbai offshore, and let's say it takes about 10 years to reach 95% consolidation. It's not far off truth. Now, I want to do the same test on the Bombay marine clay in the centrifuge at 100 G. Then I'll say, right, 10 years, 365 days, 24 hours, 60 minutes, 60 seconds, divided by 100 square. Yeah, just substituted the numbers. Nothing fancy. Then, if you work the numbers, that turns out at about 9 hours, 8.8 hours. So, what I just did means that I can predict what the Bombay marine clay is going to do in 10 years' time by running my centrifuge for about 9 hours. Now, this is what is the definition of time machine, isn't it? You are telling what's going to happen in 10 years' time now. That is your time machine, or closest in geotechnical engineering, you're going to come to time machine. So it's great. So for problems that are diffusion based, this works great. For problems where you need to apply force or energy, it all works in our favor. Similarly, seepage flow, we can do this. You can use the Darcy's law and show that the seepage flow actually is n times larger in the model compared to the prototype. This is where you need to be careful. I included this because it doesn't work in our favor. The seepage velocity in the model is n times larger than the actual seepage flow velocity in the field, which means that you must make sure that the actual velocity in the model is small enough that you get this small enough Reynolds number. So you make sure the Reynolds number is the same in the prototype and in the field. They won't be exactly the same value, but both will be in laminar range rather than turbulent range. So we can get around that. There are some limits on centrifuge testing as well. We've got about 10 minutes, I believe. 10 minutes, right? Yeah. So some of the limitations are, how far can you push this? And let me give you an example. Suppose you want to model a pile. The pile I want to model, for argument's sake, is half a meter in diameter, 500 millimeter standard concrete pile. Now I want to model this in the centrifuge. I can do it at 100 G. Then the diameter of the pile will be 5 millimeters. Suppose I do it at 200 G, it will be 2.5 millimeters. What we're saying is by increasing the G, I can basically put a knitting needle into the ground and call it pile. That doesn't feel right, does it? Somehow pile needs to be a bit bigger. And you're quite right in thinking that, because if I have a needle, the number of particles that are in contact with the needle will be maybe 2 or 3 soil particles. Whereas a real 500 millimeter diameter pile will have thousands of particles in contact around it. Now, both are not the same because I can move individual grains easily. So, this thin pile won't do the same as the large pile, although you got the right stress. So, that's because we made the G so high, we are starting to violate the principles of continuum mechanics. So the funny thing about soil mechanics is we all know that our particles are individual particles, but all our theories come from continuum mechanics. We somehow, for the 50 years till now, we managed to bridge across that and say theories developed for continuum mechanics um, can be applicable for soil because we measure gross properties. And it's the same here. You just need to make sure that your pile is of reasonable size and you got enough particles in contact. So don't do this test at 150 G, do it at 50 G. Then you got 20 millimeter diameter pile and then you got enough particles in contact. And there's a guy called Tatsuoka who came up with shear band theory to and counted how many particles are needed to form the shear band. And he said at least 15, 20 particles must be there. So as long as the ratio between the pile and the number of particles is about 15, you'll be okay, or greater than 15. So I've done all that. I don't want to do that. You can basically match for geoenvironmental problems as well. There's one thing I wanted to do, which is modeling of models. Now, there are situations where it's not possible for us to derive scaling laws as easily as I have shown you. For force, consolidation time, we could derive them easily. But there are problems in the world where, for example, cracks are forming in the ground, and you want to get there, or ground or ice even, and you want to capture that properly. But for this, the scaling laws are not known. In fact, the slides I skipped, there were two professors in Cambridge. One was my professor, Andrew Schofield, and the other one was called Andrew Palmer, who's a solid mechanics professor. They were both interested in cracking of ice because of Arctic ice and melting and hitting installations in St. John's in Canada. And the professor in solid mechanics said the scaling law should be n to the power of 1.5, and my professor said it should be to the power of n to the power of 1. And they're both big professors, and we couldn't quite argue who is right and who is wrong. But luckily, centrifuge testing allows you to a way of verifying the scaling laws itself. Okay, and that is called modeling of models. To demonstrate this, what I've chosen here is an embankment 5 meters high, sitting on soft clay 4 meters thick, and bedrock below. Okay, that is the prototype problem we're looking at. We can quite easily do 2 tests. So that is my prototype, and I can scale this at 75G or 100G. If I do it 100G, the embankment is 50 millimeters high, 40 millimeters of soft clay. And if I do it 75G, this is 67 and 53. So I can do both tests, right? Now, if I do this, oh, by the way, let me ask you a quick question. Which of these model embankments do you think will settle more and which will settle less? Just as a guess. Come on. This is at 75G, that is at 100G. Which one will settle more? You got to speak up. I'm a bit deaf. 100 G1 will settle more. Right. Everybody makes the same mistake. The settlement here would have the scaling law for settlement will be, it's a length dimension, will have a factor of n, right? Because it's the same as the length of the thing. Settlement has the same dimension of meters. So if I have settlement, say this has a settlement of 2 millimeters, the prototype will have settlement of 2 times 100, 200 millimeters. Agreed? So this 75G1, if my scaling law is right, should settle more so that when I multiply the settlement number by 75, I'll get the same 200 millimeters, right? So this one will show you more settlement. Agreed? So it's kind of fun to do this. If you actually do the test and both gave the numbers, when you scale up, they match, then you know the scaling law for length is right. So we can go do this kind of thing for each of the parameters or any unknown scaling factor and derive the scaling factor using the centrifuge itself by doing tests at different G's. And this is what is called modeling of models. Okay? And that is another nice thing to know. I think. Yeah. So here are some numbers. So 100G 3 millimeters will give you 300 millimeters, whereas the 75G one will give you more settlement, 4 millimeters, multiplied by 75 to give you the same 300. There is another fun thing as well. It's not the ultimate settlement only. The rate of settlement is also going to be different. Can you think about a little bit? This is going to hurt your brains a bit when you think about it. So normally the settlement characteristic for consolidation problem should be something like that, right? It will be an exponential decay curve. Yes? So if that is the prototype, how does this look for 75G and 100G? You think? Because this is time, this is settlement, right? But the 75G1 will scale as 1 over 75 squared. I don't know if you can see this or not. Whereas the other one, the time scales as 1 over 100 squared, right? So this is something you probably want to sketch when you go back to your room and see how should this curve look so that when I scale them up, I'll end up with the same thing. So not just the magnitude, the temporal variation or time-based variation also changes. Has to change. There is no question because we know consolidation we already derived the x-axis should scale as 1 over n squared. And if that scale factor is different, I know the final pressure I get to and the initial pressure should be same, but the curve they follow will be different. Yeah? So the rate of consolidation will be quicker for 100G test compared to the 75G test. Okay. I think that's all I wanted to do. Yeah, just to wind up, it's what the advantages of centrifuge modeling are. We create prototype stresses and strains, which means we capture true behavior. No argument there. There's no argument by any professor anywhere in the world. We have now sufficient evidence. Using centrifuge modeling, we can test new materials for which we don't know the stress strain behavior, or we can test the materials under loading regimes which we don't know their behavior under. Example, earthquakes. The biggest advantage of centrifuge modeling is it will always capture the true failure mechanism. The rest of the course, the GIAN course, we are talking about how piles fail in liquefying soils. And the reason I'm so confident to offer a lecture course like that is because I'm confident that when we do these experiments, our centrifuge test will capture the right failure mechanism. And we are having great fun going through buckling of piles and the rest of it this morning. Also, the doing centrifuge test means you're capturing the true three-dimensional behavior. Even today, you can run 3D finite element analysis, but they take quite a long time and give you a lot of complicated information which we can't understand. But because these are physical models, the true 3D behavior has always been available for centrifuge modelers. Soil structure interaction is automatically captured. So if I have any structure in my soil, the interaction will be automatically captured because it's all physical. Consolidation times are low, forces are small, energy is also small. The reason I didn't put energy is that is one of the reasons why centrifuges were built to start with is to look at blast effects. So close to Operation Sindoor, I didn't want to go into blasts and the rest of it. So let's be civilian and civilized and stop there. But it also can do that very well. Any questions? Either I'm a very good lecturer or you didn't understand a thing. There are only two reasons why there won't be any questions. It's all new for you, right? You haven't seen anything like this before. So it's quite natural that you should have questions. And don't feel shy, I'm not going to bite you. And my teeth are quite old, anyhow. Even if I bite, they don't sink in.
Yes, sir. I have a question for regarding the pile material stiffness scaling.
Yeah?
How can we do it?
Okay, easy. Say you're interested in bending of pipe. Yeah? Like what we've been talking. Get rid of this. So in the model and in the prototype, you want the same EI, right? So this is my flexural stiffness. Say you have steel pile, 500, yeah, millimeter dia with some wall thickness, 2 millimeters. That'll be probably more, 5 millimeters. Yeah, you can work out E steel and I steel pile for that, which is pi by 4 d outer squared, not squared, 4 di, something like that. Yeah. So you know this, you work that out. Now on the model side, say I'm going to make an aluminum pipe. So E aluminum and I of the aluminum pile similar, but my pile let's say is D outer is 20 millimeters and D inner is 16 millimeters. Yeah. So I can work out this and this will be for at model scale. So then I scale this up by factor of 4 to work out what the EI is and make sure that is same as this. That's it. If I do that, my flexural behavior will be matched perfectly.
For flexibility, we have to match.
Match that. Similarly, if you want to match the axial stiffness, you go to do E times A. Look, you can't do centrifuge modeling not knowing mechanics, but these are easy, right? So we can choose the material, choose the section to do that matching. Straightforward. Anything else? Yeah.
So if we are doing centrifuge modeling, or let's say account of earthquake, if we're doing this for earthquake, will the what's the relationship of n? If we increase n, does it help?
Very good question. I'm going to do this as part of tomorrow's lecture. If you are very keen, please ask the professor and come and join. Are you an undergrad here? Yeah, come to that lecture. Skip whatever lecture you have at that time and come to my lecture. Yeah, we'll do the dynamic centrifuge modeling separately. That's a totally different beast. I'm on recording, right? Maybe I shouldn't advise students to skip their classes. Anything else? This is all fun stuff. That's why I wanted to do this topic for the combined audience, because there's no complicated maths or anything here. We just went through what we already know. It's just a way of thinking. And I hope you found that interesting. Engineering is like that. Problems can be complex, but solutions and the way we think about it should be simple. That's been my motto all through. I do apologize for my groggy voice, but there you go. You get what you get. Too much Amritsar lassi, I think. Okay, we'll stop there. Thank you.
He is covering too much. Suppose length of pile is 10 meters, you have performed the test at intervals of 1 meter, so you will take average value. So average of observed n values along the length of pile. N2 is average of observed n values near the pile tip. So n values within this portion, we will take average of those values. Okay. Let us say this is 3-4 meters, we have 3-4 values, so we will take average of those n values. Now point load, how we calculate point load? For point load calculation, we will use N2, n values which we have recorded below the tip, those values we will use for calculation of point load. So corresponding to N2, first as per IS 6403/1981, if we see from that figure is also there from this figure. This is figure as per IS 6403/1981. From this, corresponding to n value, we can see the phi value. Okay. So corresponding to n value, we can see. So NQ first, for NQ, first obtain phi value corresponding to N2 from that IS 6403/1981. Then corresponding to that phi value, we can calculate NQ from the table, whatever phi value you will get. Then NQ from table 1 IS 6403/1981. I am talking about IS code only. So this table we will see. So let us suppose your phi value comes out to be 30. So corresponding NQ value you can see from this table. Okay. So then when you know NQ, then you can calculate point load. Sigma V dash NQ minus 1 into base area. Sigma V dash is effective overburden pressure. As I talked about effective yesterday, that is, if it is below the water table, then you will take gamma submerged. Okay. So sigma V dash NQ minus 1 into base area of the pile, that will give you point load. Then for skin friction load Fs into As, that you all know, K sigma average dash tan delta into As. This is for cohesionless soil. We are talking about cohesionless soil only first. So K sigma average dash tan delta As. Phi is obtained from SPT values N1. When we performed SPT, we have two set of n values, one along the length of the pile, another set below the tip of the pile. So along the length of pile, whatever n values we obtain, we will take average of those n values corresponding, that is n1, then phi value we will see again from same IS 6403/1981. K value, K varies from 1 to 3 for loose to medium sand. For loose, if it is loose sand, then we take 1. Then as density increases, one table is also there, that I will also show, but approximately we take like this. And critical depth criterion should be applied for calculation of effective overburden pressure. You know critical depth criterion, most of you. Critical depth criterion is that overburden pressure will not keep on increasing with the depth. It increases continuously like this only up to depth d dash. The d dash may be 15 to 20 times the pile diameter. So we can't take it gamma into d. Instead of taking gamma into d, then there will be very high value. Practically it was observed that it becomes constant in case of sand only, not in case of C5 soil, not in case of clay, only if it is cohesionless soil. Then this becomes constant beyond certain depth, that is approximately 15 to 20 times the pile diameter. So accordingly QS we will calculate gamma d dash by 2 if we average, sigma average dash we have to take. Sigma average will be 0 plus gamma d dash by 2 for this portion, for this length. For d dash length, it is gamma d dash plus 0 divided by 2. So gamma d dash by 2 is sigma average into K tan delta into perimeter into length of pile. Only this much length of pile we are considering first, because sigma v average we have taken for this only. Sigma average we have considered for this length, gamma d dash and 0. 0 plus gamma d dash by 2 we have taken this sigma average dash K tan delta perimeter into this length of pile. For remaining length, for remaining d minus d dash, perimeter into length is d minus d dash, average, sigma average is gamma d dash, it remains same, gamma d dash plus gamma d dash by 2. So that is same, gamma d dash K tan delta perimeter into this length, where overburden is same, constant. And point load will be not gamma d, because at the tip of the pile we take the value, but here at the tip of pile normally people take gamma into d if no critical depth criterion is applied. But considering critical depth criterion, it will remain constant beyond this, so it will be gamma d dash. Instead of gamma d, it will be gamma d dash into NQ into base area. For K values, this table is also there. Otherwise, you can take 1 for loose sand, 3 for dense sands, and for medium type you can take 2. Otherwise, you can use this table also. Bronx has given this table for steel pile depending upon material of pile also. For steel piles, delta is taken 20 and K value low relative density 0.5, high relative density 1. Similarly, for concrete 0.75, 1, 0.75 we take delta, and 1 and 2 for low and high relative density K value will be taken. Similarly, for wood 1.5 to 4. Now that is based on SPT data. Now let us suppose we have performed SCPT. As Professor Gopal Madhavushi was saying that in UK they are not relying on SPT. SCPT is definitely more reliable, because in case of SCPT no borehole is made. Only we penetrate the cone under static loading, no dynamic load is applied. In case of SPT, we throw 65 kg hammer time and again. So vibrations are there, disturbance will be there. And earlier also by making borehole, there are disturbances. Soil is disturbed when we make borehole. In static cone penetration, no dynamic load is applied and no borehole is made. But drawback is that you will not get any sample. You will not come to know what type of soil strata is there at different depths. So that drawback is also there. So normally for important works, what we recommend that both the tests we should carry out. SPT also, SCPT also. From SPT we will get soil profile also. SCPT, that will give better results. Cone penetration resistance. So make plot of cone resistance QC versus depth. As I told you yesterday, first only cone moves in the first stage. When cone is penetrated, only cone moves. Then after about 40 mm, then that friction jacket assembly and cone, they move together. There is one arrangement made in that. If you have seen that static cone penetration apparatus, one arrangement is there. You move that knob to the other side. After first seating of 40 mm, then change the knob to the, move it clockwise. Then both they will move together with the application of load. Cone and friction jacket assembly, both they will move together. When they both move together, then resistance offered will be both for cone penetration as well as for skin friction. So that will give you total resistance, total load. Then difference of the two, that will give you skin friction load. Then it will again come back to the previous stage. Next load when applied, then we will move that knob again back. Earlier it was moved clockwise, now that knob will be moved anti-clockwise. Now only cone will move for next 40 mm and so on till you reach the desired depth. What is the desired depth? Desired depth is expected length of pile plus, actually for single pile we say D or 2 times D, but actually never we use single pile. Piles are always used in group. So in group of piles, what is the width of group? So whatever is the width of group, minimum up to that, or preferably 1.5 times the width of the group. If spacing between piles is say S, center to center spacing S, then if there are 4 piles, so 3S plus D, that will be width of group. So 3S plus D, at least below the tip of the pile we should go in, because we use piles in groups, never we use single pile. So determine average cone resistance over the range of depth. Let it be QC1. So QC1 into base area, that will give you point load. Now determine the average cone resistance along the pile shaft. Let it be QC2. As earlier, we were having N1 value and N2. N1 was along the shaft, N2 below the tip of the pile. Similarly here, along the shaft, we have written QC2 and at the tip, that is QC1. So QC1 into base area, that will give you point load, and this QC2 will be used for calculation of skin friction load. Then from QC2 we will calculate skin friction load approximately by using this equation QC2 by 200. This is for driven concrete pile. For driven concrete pile, skin friction load is QC2 by 200 into surface area, and for driven H piles, QC2 by 400. So that will be on lower side in case of H piles as compared to concrete pile, driven concrete piles. Now total load then will be QU upon factor of safety, normally taken 2.5. Now in case of cohesionless soils, if piles are driven, then there will be compaction of the surrounding soil. Surrounding soil gets compacted within 3.5 d distance, up to 3.5 d from the center of the pile. That area gets compacted, that soil, surrounding soil gets compacted. So because of that, densification of soil will take place. Because densification takes place, phi value will increase. So phi value, we let us say earlier, before driving the pile, if value was phi 1, now it will become phi 2, which is phi 1 plus 40 by 2. 40 is very high value of phi. If you see the table, you will see NC, NQ, N gamma values are very high if phi is 40. So phi 1 plus 40 by 2 is recommended if we are driving the pile in cohesionless soil. Okay. So for bored and cast in situ piles in cohesionless soils, then there will not be any densification of the surrounding soil, because we have earlier we have not removed the soil. Whatever sand was there, that was there. We have not created any cavity. We have not created any hole while driving the pile. Only then surrounding soil gets compacted. When you are making borehole, then you are not adding additional volume. When no additional volume is inserted, no surrounding soil will not get compacted. No densification will take place. So in that case, phi 2 and phi 1, they will remain the same. Whatever phi was before the insertion of piles, that will remain the same in case of bored piles. For driven and cast in situ piles, if tube is left into the ground, then that is considered a driven pile. And if tube is withdrawn, then case 2 will be followed. Then this case will be followed. If we leave the tube inside casing pipe, then it will be considered as driven. Now, for cohesive soils, CNCAB, CNC will be point load. Point load is CNC into base area, and friction load alpha CU bar into AS, skin friction area, surface area, alpha CU bar AS. So undisturbed shear strength of clay at the pile tip. Driven piles cause displacement of soil. Due to this, pore pressure get increased, which reduces effective stress, and therefore skin friction capacity will be smaller. So Tomlinson recommended charts for getting the value of alpha. So alpha value, normally we say for stiff clays we can use lower value. What value normally we use for stiff clays? 0.3, and if it is soft clay, then we consider that it will not stick to the pile. Soft clay, in case of soft clay, we get soft clay will stick to the pile, then adhesion will be more. Then alpha we take 1. If it is stiff, then it will not stick to the pile, there will be gap created. So then alpha is taken 0.3. So that is approximately value. But Tomlinson has recommended like this. He has given these tables. If your soil strata is like this, here you have sand or sandy gravels in the upper portion, and your this stiff clay length, this length of stiff clay strata is LF. Then accordingly you will choose the curve LF less than 20, this dotted line, LF 20B, this LF is greater than 40B. So he has given average 100 shear strength CU and adhesion factor. Corresponding to this, you can see adhesion factor. Similarly, if instead of sand here we have soft clay, then you will use these curves. These are if it is sand in the upper layers. If it is soft clay in the upper layers, then these curves will be used for calculation of alpha. Similarly, if it is total stiff clay, whole strata is stiff clay, then these curves will be used for calculation of alpha. So Tomlinson has recommended that alpha should be used depending on the strata. Not like if this is stiff clay, always we can't use 0.3. In all the cases it is stiff clay, but depending upon the upper layers, alpha will change. Now these charts, they are essentially applicable to piles carrying light to moderate loading driven to a relatively shallow penetration into the bearing stratum. Still there is limitation. If we use these curves, these charts are essentially applicable to piles carrying light to moderate loading. For light to moderate loading driven to relatively shallow penetration into the bearing stratum. Where heavy loads are carried, the piles may be driven very deeply into the bearing stratum. For such cases, ultimate bearing capacity of pile should be calculated by using F into alpha P instead of alpha. Here we will use F into alpha P. So not always use alpha. That is very rough estimate. Then Tomlinson, for up to medium loads, he has given charts. Still for very heavy loads, we should use F into alpha P. Now what is this F into alpha P? F and alpha P are calculated from this. F will be calculated from this curve. Peak adhesion factor alpha P versus Cu upon sigma V dash. We will calculate from this alpha P, and F will be calculated from these curves. Depending upon length of fill LF upon B, you can calculate the value of F. This F and alpha P will be used in case of heavy loads. Okay. Length of stiff clay stratum thickness.
Previous chart also given by Tomlin. Previous chart was also given by Tomlin.
These charts? No. These are not given by Tomlinson. These charts are given by Tomlinson. These charts I couldn't mention. These are not Tomlinson charts. Someone, huh? I don't remember. I should not say some wrong thing, but I don't remember who has given these charts. But these are not of Tomlinson. Okay. Similarly, then for C5 soils, we will combine. Now, suppose we have this type of case. We have weak soil. This is dense sand. Then again weak soil. Now, if this gap, if your toe of your pile and weak soil, this gap, let us say H, if this H is less than 10 times the dia, then this weak soil will affect the load carrying capacity of the pile. If this gap is more than 10 times the dia of the pile, then this weak soil will not affect. Otherwise, weak soil will affect. So to consider that effect, we will calculate Q0, QL, their ultimate base resistance of pile in lower weak. This Q0 is in the lower weak soil. Considering that pile is resting on this, we will calculate base resistance. We will calculate base resistance of this strong layer, that is say QL. Then actual point load will be calculated using this equation. QP will be Q0 plus QL minus Q0 upon 10B. So when H is equal to 10B, our answer will be QL. When H is 10B, then answer is QL. Then only this soil will burn. Otherwise, effect of this weak soil will be considered in calculation of ultimate load. Pile groups, similarly in pile groups, skin friction load, length of pile into perimeter of group. In that case, we will take perimeter of group. Earlier we have taken perimeter of one pile. Similarly, QB into area of group, base resistance into area of group minus whatever soil was there between the group of piles, that will act in downward direction. So that will help in lowering the pile in downward direction. So we subtract that. So minus gamma L into Ag, that weight of soil will be subtracted. Now we will talk about settlements. So that was ultimate bearing capacity calculation. Now settlement. On the basis of imaginary raft, preliminary estimate of settlement of a pile group in sand can be made from SPT or SCPT data, as we do in shallow foundations. How we consider raft foundation? At 2/3 of the length of the pile, fictitious footing is considered, and fictitious footing is considered at the ground level. Both the cases are considered. Once we consider it at the ground level, we consider that raft foundation is there at the ground level only. Then how we calculate settlement in case of raft foundation? IS 8009 we use, these curves we use. Width of footing, in this case that will be width of pile group. If it is 4x4 group, 3S plus D. This B will be 3S plus D. So let us suppose your 3S plus D is 3 and SPT you have performed. After performing SPT, your N value is say 20. So corresponding to that, you can see the settlement. This settlement will be in meters per kg centimeter square, kg per centimeter square. For 1 kg per centimeter square, or you can say for 100 kilonewton per square meter of load, this will be the settlement. Let us suppose this is 0.01, 0.015. So about 15 mm settlement approximately for this case which we have assumed. So 15 mm settlement is for load of 100 kilonewton per square meter. So in that case, if we have say permissible settlement of 45 mm, so we can say that we can apply 300 kilonewton per square meter of load on that pile group. 15 mm settlement, that is for 100 kilonewton per square meter. So if it 45 mm is allowed, then linearly we consider it 100 into 3. 15 into 3, 45. Similarly, 100 into 3, 300. So we can apply load up 300 kilonewton per square meter for 45 mm settlement. That will be from settlement considerations. Other one you have already calculated. So whichever is on the lower side, that will be considered as ultimate load. Similarly, if you have performed SCPT, then you have to use those curves as given in IS 8009. They are for shallow foundations, but when imaginary raft is considered, so it becomes shallow foundation case. So that can be used. So from that you will calculate settlement. Now if SCPT is performed, propose a procedure based on SCPT for settlement calculation. De Beer and Martin's procedure is C equal to 1.5 QC upon sigma naught. QC you have calculated, average QC value, sigma naught overburden pressure, effective overburden pressure. 1.5 QC upon sigma naught will be compressibility coefficient. Further, Meyerhof, these were given by De Beer and Martens in 1957. Then Meyerhof in 1965, he observed that it gives very conservative results. Then he modified C value. Instead of taking 1.5, he recommended that we should take 1.9. Otherwise, very uneconomical design we get. So he modified it to 1.9 QC upon sigma naught. Now, how to calculate settlement? Using this equation. C you have calculated. C you have calculated either this, if you are to not to take more risk, then you can take De Beer approach. Sometimes Meyerhoff's, this will give a little bit more reliable, more safe value. That is more safe, this is less safe. Okay, you see, because C is in the bottom, the denominator. So S you can calculate 2.3 H upon C, C which you have calculated on the previous slide, sigma naught plus delta sigma into sigma naught. This you know, delta sigma. What is delta sigma? Hmm? Due to the application of load. Okay, load which you have applied on that column, say whatever load is coming, we will, how we spread it, 2:1. So accordingly we will distribute the load at different levels. Suppose we have different layers, we should divide it to layers. Layers will be made. For first layer you will take average QC value. For second layer you will take average QC value. You have so many QC values along the depth or along the length of pile. So you divide it into number of layers, sub layers. In each sub layer you will take average value of QC. That QC average value will be used for calculation of C. And corresponding to that H value, whatever is the thickness of sublayer, that is H. So H will be thickness of sublayer. If your total thickness which you are considering is say 10 meters, you have divided into 5 parts of 2 meter each, then H1, H2, H3, H4, H5, 5 sublayers you have. This H will be H1 corresponding C value, then H2 corresponding C value, because corresponding C value will be different. For this H1 you have different QC values. For next H thickness, next sublayer you have different QC values. So average you are to take for that particular sublayer only. So accordingly then you will calculate delta sigma at the center of each sublayer. At the center of each sublayer you are to calculate overburden pressure, that will be sigma naught. Then Q load, let us say you are applying, width of footing which you have assumed, that is BG, let us say width of group, width of pile group 2S plus D, 3S plus D, like that. So that is BG. If it is square group, then B into B. So Q divided by B into B, that was at the top. Then as you are moving down, so it will become 2:1 distribution you are to do. So whatever height is there, that height will be added to BG. Okay. Let us say up to the center of first sublayer it is Y1, so it will be BG plus Y1. For next it will be BG plus Y2. You will divide it with BG plus Y1 into BG plus Y2 and so on. Accordingly you will get different delta sigma values and calculate settlement for each sublayer, then sum up all, that will give you total settlement of all the layers. That all right. Settlement of pile group in sand. Common practice of estimating settlement of pile group in sand is to extrapolate this from the settlement of an individual pile measured in a load test. Another method is one method based on SPT or SCPT I have told you. Other method is perform pile load test on single pile. Perform pile load test on single pile. Then from single pile load test data, we have one SG upon SI versus BG curves are there. This curve is there. Based on different experimental observations, this curve has been provided. From you can use this curve to get SG upon SO or SI, that is for single pile. Settlement of single pile and settlement of group, that ratio you will get from this corresponding to your width of group. If width of group is say 3s plus d or 3 meter, 4 meters, corresponding to that you can see this value, that will be settlement of group divided by settlement of individual pile. Now if you have performed pile load test, single pile load test, then SG you can calculate, because ratio you have SG upon SI, you can calculate SG by multiplying that factor with SI. So best is for very important structures, we should perform pile load test on group. Best result you will get in that case, group pile load test. But group pile load test is very difficult to perform because huge reaction is required, because reaction for one pile resistance is very high. To create reaction for one pile load test, single pile load test is very difficult, and for group it is very difficult. Very big size concrete cubes, they are normally used. If you have seen sometimes for pier load test, they perform pier load test on flyovers. So very huge size concrete cubes they use for placing the load to provide reaction in that case. So for very important structures, group pile load test is performed. Otherwise, single pile load test if we perform, that will be used, and SG upon SI we can calculate from this, and from that we can calculate settlement of the group. Now, if you are not in position even to perform single pile load test, then so this is the equation derived from the same curve. You can use that curve for calculation of SG upon SI, or you can use this equation for calculation of SG upon SI. Meyerhoff has also given another equation which can also be used. Now, if you are not having even single pile load test data, your project cost is not allowing you to even perform single pile load test. In that case, you can calculate settlement of single pile theoretically. Some empirical formula is given. Empirical formula is given. SI equal to B by 1000 plus SE. SE is elastic settlement, elastic compression in mm. This is 1000 QL upon AE. Normal equation which you use in solid mechanics, PL upon AE. From that only SC, Q load applied, QL upon AE, where L is pile length in meters. Here 1000 has been used. 1000 has been used, and other units should be same, whatever written here. A will be in square meter, L will be in meters. Then settlement you will get in mm. That's why 1000 has been used, because otherwise answer will be in meters. So settlement you can calculate from this. Settlement of single pile, if you are not having even single pile load test data, you can calculate from this equation. So rough estimate you will get, and from SG upon SI you can calculate settlement of the group. So like this we distribute the load. Already we talked about this. So at 2/3 of the length of the pile, fictitious footing is assumed, then load is distributed, 1 horizontal to 2 vertical. So it will be distributed at the center of each sublayer. Then you calculate delta sigma. Delta sigma, let us say here, you will calculate Q, whatever load, divided by B plus D into Z plus D, that will give you delta sigma. Now consolidation status in case of clay, in case of clay, that we were talking about cohesionless soil. Now in case of clay, when performing consolidation analysis, we need to compare pre-consolidation stress sigma C dash with initial vertical effective stress sigma Z0 dash. First we need to compare these two values. This is initial vertical effective stress. Initial vertical effective stress we will calculate before the application of load. We will calculate gamma Z. Wherever water table is encountered, gamma dash into Z. So we will calculate sigma Z0 dash. Sigma C dash pre-consolidation stress, that procedure you know, three procedures are there. Sackmartman method is there. You can, using those methods and performing test in the lab, E log P gauge, you can calculate sigma C dash. Now you are to compare sigma C dash and sigma Z0 dash calculated, while sigma Z0 dash is determined from effective overburden pressure equation with the original field conditions and original hydrostatic pore water pressure. Both values must be determined at the same depth from where the sample has been collected for performing lab test for calculation of sigma C dash. Let us suppose you have collected clay sample from 5 meters. Then sigma Z0 dash you will also calculate at 5 meters. Gamma into Z, that Z will be 5 meters. If you have collected sample for performing the lab test for calculation of sigma C dash at 5 meters, that sample, so both should be at the same level, same depth. Only then you can compare. Then you compare sigma Z0 dash with sigma C dash. Now if sigma Z0 dash is equal to sigma C dash, then it is normally consolidated clay. So if sigma Z0 dash is equal to sigma C dash, then it is normally consolidated clay. But because we collect the samples, there are so many errors in collecting the samples, there are so many errors in performing lab tests. So these values normally they will not be equal. So it is recommended that even if these values have error of plus minus 20%, we consider that they are equal. Let us say sigma Z0 dash is 100 and other value is 80 or 120, even then we will consider that they are equal. We will consider the clay as normally consolidated clay. Over consolidated if sigma Z0 dash is less than sigma C dash. This condition, that is pre-consolidated or over consolidated case, and if sigma Z0 dash is more than sigma C dash, then soil is under consolidation, under consolidated soil. Now for normally consolidated clay, you will use this equation, HCC upon 1 plus E0 log 10 sigma ZF dash upon sigma Z0 dash. This equation you will use for calculation of settlement. This is for normally consolidated clay. Now if it is over consolidated clay, then further there will be two cases. Let us suppose your sigma ZF dash is less than sigma C dash. If sigma ZF dash, what is sigma ZF dash? Final load which you are applying. Sigma C dash is pre-consolidation, pre-consolidated pressure. If final load, let us suppose earlier 3-story building was constructed on certain soil. Now that is demolished. New building you are going to construct, that is say 7-story. So sigma ZF dash will be high. So if your sigma ZF dash is more than pre-consolidated pressure sigma C dash, this case sigma ZF dash is less than sigma C dash, or this is sigma ZF dash greater than sigma C dash. So if it is less, sigma ZF dash is less than sigma C dash, so then throughout soil will be reconsolidated. Soil will be reconsolidated throughout because sigma, both initial pressure and after the construction of the building, So earlier building was say 7-story, now you are making only 3-4 stories. So sigma ZF dash is smaller than sigma C dash. So in that case, throughout soil will remain reconsolidated. So CC value which you were earlier you were using this CC compression index. Compression, if you remember E log P curve, this E log P curve, first round of loading, then you release the load, then you reload. It will not follow the same path. So reloading curve that will be used for calculation of recompression index. Then you will not use CC, not compression index, you will use recompression index. So recompression index here CR will be used. So if your soil is not loaded fully to the load up to which it was loaded earlier, then it is throughout it will remain reconsolidated case. So then this equation will be used. Normally consolidated CC will be used. If sigma ZF dash less than sigma C dash, then reconsolidation. Now if your sigma C dash is less than sigma ZF dash, that means up to sigma C dash, you are reloading the soil. Beyond sigma C dash, load which you are applying beyond sigma C dash, that is not reloading. So reloading is only up to sigma C dash. So final stress here, final stress we have used, here final stress sigma C dash, for that it is CR. Beyond that, from sigma C dash to sigma ZF dash, it is first time loading. So it will be compression index only. Is it clear? So like this figure.
Previous time.
This one?
Are these 20%? Do you have preference for this one? Do you have preference for this plus minus 20%?
That's what I said, because there are some errors in collecting the samples. Totally undisturbed sample cannot be collected. So further there will be some errors in performing the test in the lab. So never, it has been observed that never you get these two values equal, exactly equal. So even if these values, they are within plus minus 20%, we will consider that they are equal, and we will consider the clay as normally consolidated clay.
Do we have references?
References must be there. Without references we can't say, but I have taken it from the book Caduto, Principles of Foundation Engineering, Caduto. From that book I have taken this. He must have given the reference from where he has taken. I have taken from that book.
Another doubt that I have from the next slide. Next slide. So that equation that you have shown just now. So here actually when the soil is decompressing, so that time also soil is completely saturated, because suppose we have constructed, because the consolidation we presume that the soil is completely saturated. Suppose we have constructed a G+5 structure, we are demolished. So in that condition the soil may be still little bit. Then again suppose we have constructed another structure, again it is going to be experienced some kind of the sediment. So the process of the reconsolidation or recompression also, the soil is 100% saturated, there is a possibility that the saturation may not be 100%.
Its saturation is different from this pre-consolidation pressure. Pre-consolidation pressure, what is pre-consolidation pressure? The load up to which soil was previously loaded in its previous history, any time. Maximum load which was applied earlier. From that you will get sigma C dash. So this sigma ZF dash is the load up to which you are now currently you are going to load. If that load is not equal to sigma C dash, that means you are not reaching that point of loading. So soil is considered as reloaded. We are reloading it.
And then I'm reloading, of course, sir, but the thing is soil.
First load was applied, then load removed, then reloading started. So that's why we get curve like this, then go back, then this. Beyond this, again we consider it virgin curve. Previous one virgin curve, this we also consider virgin curve. Only this portion we consider reconsolidation. So that's why we could take reconsolidation, recompression index.
So in the process of deconsolidation, the soil is 100% saturated. That is not relevant.
I don't think so. Why 100% saturated? Not necessary. Whatever water will be there after the application of load, that water will start moving out. Settlement happens. So why it will be always 100% saturated? I don't think so.
Because in the consolidation process, generally we need that soil is.
No, that is for performing the test only. We consider it. Actually, in the field, we will not find always clay is fully saturated. Some saturation will be there, then load is applied, pore water pressures are developed. Slowly and slowly, those pore water pressures will start dissipating. That dissipation results in settlement. That is the actually phenomenon of settlement. So, if we have time, I can talk about some uplift capacity also. What's the time? Almost 3 o'clock. Uplift capacity, we can talk about little bit. Because piles are subjected to uplift forces. In case of foundations of tall chimneys, transmission towers, jetty structures, resistance to uplift is given by friction between pile and surrounding soil. It may be increased in case of board piles by underreaming or by belling out of the bottom of piles or by bulb bend of a driven and cast in situ pile. So this is nothing but skin friction load, you can say. Uplift resistance is, so skin friction alpha Cu into surface area, K sigma average tan delta into surface area. This is for sand part, this is from clay contribution. So Meyerhoff and Adams, they have developed some expressions for computing uplift capacity of bulb pile. In cohesive soils, based on mobilization of shear strength along the cylindrical surface above base diameter, they have given this equation. This, instead of alpha, they have used symbol MF, that is one and the same thing. MF is equivalent to alpha only, alpha CUAS plus WS, weight of soil, and WP, weight of pile. This WS is weight of soil in the annular portion, because bulb has been made, because okay, bulb has been made, this is WS. In this portion, whatever soil is there, this annular portion, this is WS, WP, weight of pile. ये चलता है. So this equation based on mobilization of shear strength along the cylindrical surface, then based on bearing capacity failure, they have given this equation 9 Cu, as we use CNC in case of piles, and C is taken as 9. So he has taken 9 Cu, pi by 4 dB square minus d square. This is diameter of the bulb, this is diameter of pile shaft plus weight of pile. But for long piles, further recommended that we should add this alpha CuAs also in this. Then uplift capacity will be smaller of 1 and 2. That will be uplift capacity. Okay. MF values they have also suggested. So approximately as we take 0.3 for stiff clays and 1 for soft clay. So approximately in that range only. So for soft clay he has given 1.1, for stiff and fissured clay 0.25, stiff clay 0.5. So these are approximate values of alpha or MF they have suggested. This figure I'll talk about based on modification of in case of C5 soil. Based on modification of shear strength along the cylindrical surface above the base diameter for shallow depths. When embedded length of pile L is less than a certain value H, referred to as limiting height of failure surface above the base. Two cases are there. I have used this L and H. This is L, length of pile, and H, certain height which we calculate. I'll let you know how to calculate. If this L, this left hand side is shows that L is less than H. Right hand side that shows that L is greater than H. So if this length of pile is greater than H, then different equation is given. If your length of pile is less than H, then different equation is given. Okay. For shallow depths, when embedded length of pile L is less than certain value H, then this equation will be used, where S is shape factor given by H ml upon dB with maximum value of S equal to S maximum. This I'll make you clear on the next slide. You see this table they have given. From this table, for different phi values, H over dV is given. From this you will get H. I told you that if H is less than L, then equation is different. If H is greater than L, so length of pile you decide. Let us say length of pile is 10 meters. Then bulb dia, that is also decided by designer. Whatever diameter of bulb is there, that is known to you. So if diameter of bulb is known, H over dV value from this you can see, say phi is 30 degrees, H over dV is 4, so H you can calculate 4 into dV. So H you can calculate, length of pile is known. Now if H is greater than L or smaller than L, accordingly you can use the equation. Is it okay? M has also been used, S maximum. These terms we have used here. H ml upon dB. M also will be taken from the table corresponding to phi value. M will be taken from table corresponding to phi value. H also H upon dB. H upon dB is given in the table. H upon dV value from the table you can take. So that is S. But S should not be more than S maximum. This S maximum is also given in the table. If S maximum is more than this, then we will take this. So we will calculate S. If S is more than this value, then we will take this value. I think it's clear now. So H we will calculate from this. Length of pile is known. Accordingly, equation will be decided that which equation will be used. H greater than L or H less than L. Both the equations he has given. M value also given, and S you can calculate using this M value and dB. Then compare it with S maximum. If it is more than S maximum, then we will take S maximum. For L greater than H, this equation is there. Now based on bearing capacity failure, this equation is used. Then one value you will get from previous equation for L, either it will be L less than H or greater than H. One value you will get from that, another value you will get from this bearing capacity failure case. Least of the two, that will be taken as uplift capacity. Just to give you some idea, you can say we have this data D 45 centimeters, length say 22 meters, Cu 40, phi 0, gamma saturated, this is given. Then if you are to calculate uplift capacity, pile has enlarged base diameter 1.125 meter, submerged weight of pile is 42.5 kilonewton, weight of pile is also given. So these values you can use MF, Cu, AS dash plus WS plus WP. You are to substitute the values. You can calculate, then smaller of the two, that will be your uplift capacity. Similarly, second case also you can have, if same problem, if let us say C is also given, that there C was 0, then different equations are there. For C5 soil, different equations are there. If C5 is given, then from the table we will see phi given is 30 degrees, H over dB from the table is 4 to calculate H. Now L greater than H, so according S equal to S maximum 1.6. So accordingly we will substitute the values. You can calculate ultimate uplift capacity. That will be smaller of the two. That will be final value. That's all from my side. Pile group, similarly pile group as in the case of piles we take. Now any question you want to ask? Thank you. Which value? No, not as per IS. IS code has not mentioned this. IS code has given underunit piles case only. Ultimate bearing capacity for underunit piles. No question, then it's okay. Everything is clear, I understood.